All right, thanks everyone for coming, both in person and virtually. We're excited today for Harry and Anthony to present our work at the GeoDAWG seminar series. Just quickly, the usual introduction that we usually give at the beginning of these seminars. All of our news and updates can be found on our website, which is the URL located at the top of the page, including the seminar schedule. Also, if you'd like to sign up for our mailing list, you can do so at the link provided. We're almost up to 200 people, which is really exciting, the community that we're developing. So please sign up. You'll get information about these seminars as well as the upcoming workshop this summer in Germany, among other things. So please do that. And also, if you have any suggestions for future speakers, if you'd like to yourself or know someone who'd be good, you can contact us via this link, and then we'll schedule them in the future. And like always, we will be recording this talk and publishing it on our YouTube page, and all of those can be accessed on the seminar link on our website itself. So you can go back and watch these at any time. Briefly, because this is a little bit different, we have two speakers today. Please remain muted at all times unless you're actively speaking. You can enter your questions in the chat or raise your hand and unmute yourself and ask them. But since we do have two speakers, we're probably going to be a little bit pressed for time. So we'd like to just quickly at the end of each talk to take brief clarifying questions and save the larger discussion for the end. And so, as I mentioned, today is the second of a two-part series. The first part was presented last month by Grant Stevens, and he presented on data mining based empirical reconstruction of substorms. That presentation can be viewed at our website. And here he detailed the data mining empirical reconstruction that will be used today by Anthony and Harry to inform first principle models. Well, Anthony will go first describing how he's using the empirical pressure to inform the inner magnetosphere, while Harry will be using X-lines to inform different regions of resistivity in the magnetotail. And Harry and Anthony are both postdocs at Johns Hopkins Applied Physics Lab, and we're really excited to have them here today and to present some of their work. So I will stop sharing now and let Anthony take it away.
All right, cool. Does that look fine for everyone? It's working?
Yep, looks great.
All right, cool. Well, thanks very much for the introduction. It's interesting being on the other side of this, but happy to be here today. It's also not very often you get to have a title this long, so I thought I would go for it. So as Adam said, Harry and I will be talking about ingesting different quantities from data mining reconstruction into first principle models, and I'll specifically be looking at embedding the empirical pressure within a global MHD model. So just a quick outline. First, I'm going to introduce the white box model that we're using, which is going to be the Gamera MHD model coupled with the Rice convection model, or RCM, in a magnetosphere model. And then we'll do a quick recap of what Grant showed last month, the salient points from that as far as the pressure reconstruction, and then talk about how we're going to combine those two into a gray box model, and then go through some results, including some interesting realizations we had in implementing the coupling, and then a quick example of the simulation applied to the March 2015 storm. Okay, so to start off, MHD modeling is used quite ubiquitously in global magnetosphere modeling. It has been used for quite a few decades now, and it does very well at the global structure and many of the regions, even down to smaller scales. But because ideal MHD doesn't include energy-dependent gradient curvature drifts, and because these drifts are extremely important in the magnetosphere, that means that MHD on its own isn't able to produce an accurate representation of the inner magnetosphere, particularly during geomagnetic storms when you are supposed to be building up a lot of pressure there. And so it's now common practice to couple MHD with dedicated inner magnetosphere models. Here in this image, I have an example from Pembroke 2012 of using the LFM MHD model on the left here on its own. You can see that there isn't really much of a intermagnetosphere pressure to speak of. And then when this is coupled with the rest convection model, then you build up a more representative, or a rig current more representative of the conditions it's being driven with. So just a quick high-level overview of how that coupling process happens. You can sort of follow along using this image on the right here. This is an image of some model data using the Gamera MHD model, which is the successor to LFM, also coupled with the rest convection model. And so first thing that happens in your coupling procedure is that you seed field lines in an equatorial grid and then trace them through the MHD domain. And while you're doing that, you use this to determine the closed field line domain and specifically where your intermagnetosphere model is, where its outer domain is going to be. And then also you calculate several useful quantities along the flux tube, including the flux tube volume. And you pass all that to the intermagnetosphere model, and in this case in RCM, it involves this distribution where it also has the extra dimension of energy, so you get your gradient curvature drifts, and then you sum all your moments up and take your flux tube average moments and hand them back to MHD. And then MHD will set those moments as a target value to adjust its pressure to over some time cadence, usually, or time scale, usually on the order of, tens of seconds to minutes long. So that's sort of at a high level how the white box modeling typically is done. And then now just a quick recap of the magnetic field reconstruction. So one of the major barriers to doing data assimilation in geospace models is that at any one given point in time, we just don't have enough data available to us because there's only a handful of spacecraft that are operational at any point in time. But the way that Nav and Grant Stevens have gotten around this is instead taking all of the magnetometer data from decades of spacecraft, and instead of sort of binning them by the time, mapping them to this 5-dimensional state space, which consists of 5 variables, including the AL index, its time derivative, the interplanetary electric field, the SIMH, and its time derivative. And so that means when you actually want to go and reconstruct the magnetic field for a certain point in time, you then calculate those 5 corresponding indices, go to your state space, and then choose the k nearest neighbors from here, and that will give you a distribution of magnetometer measurements throughout your magnetosphere. And this ends up using about 1% of the total magnetometer archive when you do this process. So now we have all these data points that are used to fit a magnetic field model, which is expressed as a basis function expansion, basically, where these coefficients here, the AN, AMN, are free parameters that we end up, or that they end up tuning to fit the data. And what you get is your final magnetic field reconstruction of your magnetosphere. And so to get to the pressure, there are a couple more steps involved. The first step is to very simply take the curl of the magnetic field to get your current density. And then from there, you can assume a quasi-static equilibrium so that you have your Lorentz force balance with your gradient of pressure. And this is a gradient pressure, but we need to get to the actual pressure itself. So one method of going about this is to integrate this quantity and assume isotropy along field lines. And then essentially what you need to do is you need to choose a starting point where you're pretty confident in your estimation of the pressure for that point. For example, here, and then you integrate inwards, you integrate J cross B inwards, and you get your pressure at the point that you are interested in. You do this for the entire grid, and you get a nice pressure distribution throughout your magnetosphere. Okay, so let's talk about how we're going to combine these two. Is on the white box modeling side, it's fully first principles in physics based, but that of course comes with some limitations. It is a very, it's a highly nonlinear and coupled system, which means it can be quite hard to balance. If something goes wrong, that can get propagated forward quite easily. And when you combine this with the fact that there's many uncertainties in the boundary initial conditions, as well as some of the model parameters that we have difficulty constraining with observations, means that it's very possible that the first principles model can get onto a trajectory that might diverge from reality unless it's corrected by data assimilation. The problem being that we haven't really been able to really correct via data assimilation prior. On the black box modeling side, one of the biggest benefits from it is that we can get a pressure distribution without having to model how that pressure distribution was generated or lost, which is really helpful because on the white box model side, it's very difficult to make sure that you're capturing all these generation loss processes correctly and balancing them to end up with the proper pressure distribution. But of course, it comes with its own limitations as well, including it's also affected by its Magnetosphere boundary conditions. It doesn't include dynamic processes in the sense that, like Grant showed last month, it can pretty accurately predict where X-lands occur. And we know that's going to lead to some dynamic processes from there, but it doesn't model those for you going forward in a time evolution kind of sense. So the black box model doesn't provide that for you. And also, as always, you can only ever extract limited physical insight directly from a black box. So our goal is to combine these two into our gray box model. And specifically what we're going to do is we are going to embed the empirical pressure within the MHD in a magnetosphere. We're going to do this by calculating the empirical pressure at a 5-minute cadence or so, or at a 5-minute cadence for the given time interval of interest of the simulation that we're going to perform with Gamera. And then that gets mapped onto an ionospheric grid along the empirical field lines so that we can use the same coupling method as usually employed with Gamera and RCM that we outlined earlier. But here instead, we're going to be ingesting the empirical pressure back into MHD. So what this effectively does is it combines data mining with data assimilation to constrain the magnetosphere pressure distribution with data, which is something that can't be achieved with only the spacecraft that are available at any point in time, thanks to the reconstruction methods of Sitnov and Stevens. Okay, so we'll take a quick look at our first attempt at implementing this pressure ingestion. The method seems very straightforward and maybe intuitive at first, where along every flux tube, the target pressure that we're going to tell MHD to ingest is simply going to be whatever the pressure the empirical model says should be there. And what ends up happening is that this is actually very physically unstable and causes these sort of constant eruptions that occur. So I'll play this video in a second. You'll see when I start one major one appear at noon here, and then another major one at dawn. We'll see the sort of eruptions explode. And then over time, if we give it a second, we'll see this constant sort of outflow you can see in this pressure plot here. And sorry, I should have mentioned, this is looking at the equatorial plane of the global magnetosphere. So these sort of constant eruptions are not very physical. The real inner magnetosphere does not do that. So there's something going wrong. And we'll go into detail exactly why in a second. But essentially, the gist of it is that in doing this coupling method up here, where we're just ingesting the pressure, we're not considering the fact that there can be a difference in the field line configuration between the empirical model and Gamera. And this is something that we never had to worry about before with Gamera and RCM, because RCM just uses Gamera's flux tube volume even throughout its own domain. So they always agreed on the field topology and just had to adjust the pressures. And that's not the case in this scenario. So to try and explain that in a little more detail, is essentially the empirical pressure that ends up getting calculated is in a quasi-static equilibrium specifically with the empirical magnetic field. And so if we take our little example magnetic field here, we have these two flux tubes in sort of orange and blue. And for a given flux tube, it has its own pressure and flux tube volume, which is B here, this integral of 1 over B. And this quantity P times B to the 5/3 or PP to the gamma equals the flux tube entropy. And so as shown in this figure here, there's a certain stability condition to the magnetosphere where the system is stable if entropy is increasing with radial distance. And now this is not a condition that is imposed on the empirical model when doing the reconstruction, but because this is the sort of general state of the magnetosphere, it sort of comes out through the magnetometer measurements and gets essentially applied to the pressure distribution through that process anyways. And so this is in quasi-static equilibrium, but what happens is when we ingest that into the empirical model is that the actual flux tubes that gets mapped onto can be different sizes. And so that means that we're neither conserving the total thermal energy or the flux tube entropy between the two models. So as an example here, if we hold the pressure constant, but the MHD flux tube volume is larger on this flux tube than in the empirical pressure, that means that the entropy is larger. And so that would show up as a little bump along here, and that would be unstable. And so that field line wants to move out until it reaches its stable position. But the real problem is that even as that field line grows and that flux tube volume grows, we're still holding pressure constant. So we're just increasing entropy even more. And so it will never reach its stable position as it keeps moving outwards, and eventually just grows and grows and grows until it erupts and reconnects and turns into an open field line where the empirical model or the intermagnetosphere coupling implementation is not sort of controlling that flux tube anymore. So it's very unstable and unphysical. And so the next logical step from there is to instead ingest pressure by equating the flux tube entropies between the two models. And so what happens when we do that is now we're also passing information about the empirical model's flux tube volume, so we can calculate entropy on the MHD side. And then in that same scenario where you have this orange field line that's larger on MHD than it is in the empirical model, that means that the pressure that's set for it is going to be lower than the empirical pressure, so that it's sort of encouraged to be compressed. And then similarly on this blue flux tube where the flux tube volume is smaller, then the ingested pressure is going to be larger, so it's encouraged to expand. And this is all going to occur while holding entropy constant along that field line. And so this encourages MHD to dynamically balance its field towards the empirical field. And what's really cool about this is that we're still just ingesting pressure on the MHD side, but by doing it through equating entropy, we're not only bringing over the pressure that the empirical model says should be there, but also sort of encouraging MHD to balance itself towards that empirical field as well, all through the pressure. Unfortunately, I will say this encourages the MHD to balance itself towards the empirical field, but it can't strictly enforce it because there's still a difference in the boundary conditions. And so you can never have exactly the same field communicated to MHD, and the dynamics of MHD will sort of disrupt this process too. So at best we can encourage. Okay, so now we'll take a look at that same simulation, but using the new ingestion method here. So as we see, there's a bit of some sort of waviest features along the outer boundary of the ingestion region, but we aren't getting those eruptions anymore. And I can jump through a little further and you can see that we're still not ending up with those eruptions. So this is a much more stable and physically consistent method of ingestion, sorry. Okay, and so just to sort of comment on these wiggles that show up here, I won't spend too much time on it, but essentially you can also see that there are these flows coming in from the MHD side that are trying to penetrate into the magnetosphere. And this is because if I show the rest of that figure that I showed earlier in that entropy stability plot, low entropy bubbles are constantly generated through a magnetosphere connection, and they show up as these, low entropy features. They're also usually about, a couple RE wide, so about the width of this gap right here. And in reality, these bubbles are, of course, unstable to the background, and they will move inward, sort of switching places with the higher entropy flux tubes below them, which is referred to as interchange. And they'll move in until they reach their stable location with respect to the background entropy profile. In the simulation, though, To put it briefly, the current coupling process has difficulty properly resolving this. I don't have a fully concise explanation for it yet, but if we just watch the video real quick, we'll see that there are these sort of fingers poking in. I should clarify that this is just looking at the intermagnetosphere model part of the domain, not the entire global magnetosphere. So this is probably about plus or minus 10 RE in X and Y, and this is looking at just the intermagnetosphere portion that ends up getting ingested into MHD in the equatorial plane. And so these bubbles that are trying to penetrate inward end up showing as these incursions onto the boundary here. We can see that they sort of will come in and then rebound off and maybe slide along the boundary and all that. And so it's just having a dynamic MHD model with a relatively stiff treatment of the intermagnetosphere makes it so that the model can't fully handle these processes. But ultimately, this is, for now, a sort of secondary effect that I at least would like to figure out how to fix, but doesn't keep us from stably ingesting the empirical pressure in the intermagnetosphere. And so I'll just show a quick example of using this gray box model on a simulation of the March 17th, 2015 storm. And so the DST is a time series, of course, but the rest of these panels are all showing their quantities at 9 UT in the storm. And you can see in the DST panel that this is right around the first DST minimum here. And so just as a recap, we're going from the empirical pressure, mapping it to the models and magnetosphere, and then adjusting that into the global magnetosphere solution here. And looking at the ionosphere, we can see a comparison between the ampere calculated field line currents and those calculated by the model, that we have pretty good qualitative agreement between the two for this time period. Especially, we can see that we're forming region 2 currents, which is a result of the ring current that we're able to ingest, and some pretty good agreement with the ampere field line currents. Now, I will admit that I chose a pretty favorable time to show for all of these, because there are times where it's not very favorable. But one of the benefits of the gray box model is that there can be earlier times where the pressure that it's ingesting is incorrect for some reason, or the effect it has on the system is a little bit incorrect. But because that isn't sort of highly coupled in the same way that the white box model is, that doesn't spoil our solution later in the simulation. So later on, when we have a better representation of the intermagnetosphere pressure, then our system can ingest that just fine and get a pretty good answer when we have good data there. Okay, so just as a recap or overview, summary, data paucity has previously prevented data assimilation techniques from being applied to geospace models, but the combination of the data mining approach to the empirical reconstruction of both the magnetic field and the pressure, that combined with the sort of equilibrium nudging ingestion method that we're using, where we're ingesting based on equating entropies rather than just pulling in pressure directly, together offer a feasible path towards data assimilation in geospace modeling. And so one of the big advantages is that the gray box model can achieve a reasonably accurate intermagnetosphere pressure without needing to model the highly nonlinear source and loss processes. Of course, in the white box model, that's one of the things that we're interested in the most, but especially at lower resolutions, we just can't expect that to happen because we're not going to resolve those features properly. And so this data assimilation method, one of the uses for it is to get a balance of faster run speed that you get with lower resolution runs, combined with an accurate intermagnetosphere pressure distribution that you otherwise couldn't expect them to achieve. So this is very important for real-time operational capabilities, having both that speed and accuracy, and also opens the door to some ensemble experiments. So now that you can get a reasonable magnetosphere at lower resolution, then you can do an ensemble of runs at that lower resolution. And just to mention again, having that dynamic MHD and stiff intermagnetosphere presents its own challenges as far as exactly how that coupling is handled. But that's sort of something that we're hoping to work on in the future one potential solution is to nudge the MHD to the empirical pressure over a longer time scale so that MHD is allowed to sort of update its state within that field line region on its own before it's too influenced by the empirical model. Okay, and that's all I have. Thank you.
Great, thank you so much, Anthony. We have maybe time for one really quick clarification question, if there is one. Feel free to enter that in the chat or raise your hand. Okay, seeing none, we will move on to our next speaker, who is Harry Arnold. So I'll let you take it away, Harry.
All right, can you hear me?
We can.
And you see the correct presentation?
Yep.
I hope. Good. Excellent. So yeah, my name is Harry Arnold. I'm giving the second subpart of the second part of this talk on gray box modeling. I'm going to be focusing on empirical resistivity in a global MHD model. So let's dive on in here. So first, I'm going to talk a little bit more about the data mining reconstructions just from the previous talks, just to outline some key points. I'll talk about using the data mining to inform global MHD simulations in a similar but different way from what Anthony was doing, using what we're calling empirical resistivity maps. I'll compare the simulation results to the data mining results, talk about the effects of this resistivity, which include the suppression of near-Earth reconnection, but also reconnection in rebounding flows near Earth. So it's sort of seemingly opposite, but they're tied together. And then I will conclude. So Anthony did a great job giving an overview of the data mining process on this slide, so I'm just going to skip it for now. And instead, I'm going to talk about the data mining reconstructions of X-lines. So this was in last week's talk by Grant Stevens, but I just wanted to remind you, or in case you hadn't seen it, they use the they do the data mining process just like Anthony described, and they recreate the Earth's magnetic field, and they can actually identify X lines and O lines as sort of sketched out in this plot in the bottom left here, and they can compare those with observed IDRs. Now, the IDR is the ion diffusion region, which you should expect to see an IDR either at an X line or at an O line. So the in situ data doesn't necessarily know the difference, but these global reconstructions do, and you can compare them. So there were 26 IDRs that have been identified, and of those, 24 were had reasonably good agreement with the data mining reconstructions. And so just as an example, there are 4 on the right here. You can see the green dot shows where the IDR was identified, and then these contours of BZ equal to 0 correspond to X lines on the Earth side and O lines on the tail side. So this one's an O line, this one's an X line. So the point is that we have good confidence that these data mining reconstructions can in fact identify X lines in the Earth's magnetotail. So, you know, where does reconnection occur? Well, the short answer is it's wherever data mining tells us. But I do want to mention here that the data mining region sort of goes out to about -30, maybe a little bit more in the tail. That's in units of the Earth radii. But there have been many statistical studies that have shown that there's this watershed region just around -30, in fact, that showed this difference between observed earthward and tailward flows. And so this suggests that there is quite possibly an X line, an extended X line that is often observed there. And in fact, what you can see is that the data mining reconstructions often show these very large, sometimes totally across the whole tail, X lines at around -30 RE. So this is sort of 2 different ideas of where reconnection occurs, but they both sort of agree with each other. So why should we even add localized resistivity to our simulations? Well, the problem with global MHD models is that they're missing kinetic physics, right? And magnetic reconnection fundamentally occurs at kinetic scales. So in in fact, really the only way to get a global MHD simulation to reconnect is to have some sort of typically numerical resistivity or an explicit resistivity. And with these global models, often an X line that is very close to Earth, say less than 15 RE into the tail, is observed. So this is an example on the right from Lenton et al. 05. The bottom one is an example from one of my simulations. Here again, you see an X line very close to the Earth. But in fact, from these Rogers et al. Papers, we know that the IDRs identified by MMS are often much further in the tail, something like around 20 RE. And there have been many other studies of this that also show that these X lines are likely to be much further in the tail. So the idea behind adding localized resistivity is to make our global simulations more realistic by having reconnection take place where, in fact, it likely takes place. So we use this global MHD model called a MAGE. Eventually, MAGE is going to couple together all of these different models. Right now, what I'm using is the Remix, which handles the Earth's ionosphere. Of course, Gamera, which is itself the global MHD model. And then also we're coupling in this data mining business from TS07D. So that's what creates the Earth's magnetosphere from the data mining. So I'm looking at one specific event. These are the solar wind parameters as well as SimH on the right, just to give you an idea. This is the time period that I'll be looking at, which is just a few hours because I'm just looking at this sort of isolated substorm. And this is when the substorm officially onsets. I'll just point out that SimH is in fact, it's very small, but it's also positive. So this is, definitely not during a storm at all. The solar wind is slow. You have BZ is initially positive, but then turns southward, right? And crucially, during this event, MMS sees an IDR, which is in excellent agreement with the data mining results. So that's really what we're interested in. So first, I'm going to show you the results from my simulations. Here on the top, we have the data mining reconstruction results. Then I have two separate simulations that I'm showing you. These middle panels are when I include a resistivity. Bottom is just your base MHD run. And then obviously the left side of all three of these panels is the meridional plane. The right side is the equatorial plane. So let me tell you what I'm showing you in these bottom four plots. We have these arrows, which are plasma flow velocities. Magnetic field lines are in green. This black contour, which appears in both the left and the right side, that's where the resistivity was placed for this simulation. And I just want to point out here that even though in reality, the X lines are, changing locations, maybe they're hopping around, maybe they're just moving tailward, whatever, it's definitely mobile. But in this simulation, just as a first attempt, I just put this resistivity there for the entire simulation. And then these red contours are contours of BZ equal to 0, which again, the Earth side of this corresponds to an X line, the tail side corresponds to an O line. And then finally, these little dots that I've included, that's an algorithm that I implemented, and maybe I'll talk about it a little if there's time, just to identify X lines. And the point here is that when we include this resistivity at this time, 1535 on this date, when MMS identified an IDR at this location, which is an excellent agreement with the data mining reconstruction of an O line, we also get an X line. In this case, it's an X line, but you can imagine it's sort of all part of the same topological feature. So the point is that by including these resistivity, we can in fact change the magnetic topology in the simulation to match observations and data mining reconstructions. And this becomes very clear when you look at the bottom panel where there's no resistivity. At this point, there's really no X line at all. You can see these field lines. It looks like a stretched tail, but it certainly hasn't begun reconnecting anywhere near this location where the IDR was identified. So this is very promising as a first try. But what I want to talk about are some of the effects of including this resistivity out in the tail. So the top plane, this is from that same simulation where there's no resistivity. The bottom plane now, though, has this large region of resistivity out in the tail near minus 30 RE, minus 35 RE. And this is just to sort of capture that watershed region, or the, where the data mining often sees an extended X line. And what we see by incorporating this region of resistivity is the reconnection happens earlier than it does when you don't include reconnection. And because of that, the X line, processes this magnetic flux from the lobes and sends it earthward. And that actually prevents the current sheet near the Earth from collapsing and reconnecting. So this is that problem that is not always, but is often an issue in these global MHD simulations, where you get reconnection that happens way too close to the Earth. You can see it, it's just about to happen. There it goes, right? So that's within 15 RE into the tail. But it doesn't happen when you include resistivity, because that magnetic flux prevents it from collapsing. And this is really in agreement with what Byrne and Hess saw in 2013. They had reconnection further in the tail that, again, prevented reconnection closer in. An interesting consequence of this, actually, even though it does prevent this sort of large scale reconnection that happens very close, what we do see is sort of these isolated, small scale, short-lived features that are, in fact, X lines that can happen very close to the Earth. So here, this is 11 RE into the tail. And this is from the simulation where we have resistivity further out. So, what's happening? If I just said that it's preventing reconnection, why is it producing reconnection? And the reason is because you have this initial flow from that further out X line that's bringing in the magnetic flux. But as it gets into the near Earth region, it rebounds off the strong magnetic field and goes tailward, actually. And this happens on both sides of this flow channel here. And when it moves tailward, because the plasma is frozen in with the magnetic field stretches, and in fact, it can reconnect. So at this point, this is where the X line is, shown by these two axes. These are supposed to be the sort of axes of reconnection. So you have the reconnecting field along this axis, the reconnected field along this axis. And I'm showing these quantities right at that point. So this is the reconnecting field, and this is the reconnected field. So you can see this dashed red line shows right when the flow turns tailward. And then the green line shows when the X line is actually observed. And so once the flow turns tailward, we're stretching out the tail, and then eventually it reconnects shortly thereafterwards. An interesting feature about this, though, is that it's very small, right? So here's our contour of BZ equal to 0. And this is a little bit bigger than an RE, maybe a couple at most. And it doesn't live very long either. You sort of reconnect a little bit, and then it bounces back and smooths out. So you do get this near Earth reconnection, but it's qualitatively different from the extended X lines that you see when you don't include any resistivity. So this is where I've actually looked at all the X lines in the simulations. Basically, all that I did was I just scanned the magnetotail for X line topology, and group them all together so that you have if your X line is extended by several RE, then it matches that. And I've plotted that for my 3 simulations. So again, on the top, this is without resistivity. The middle panel here, this is where I placed resistivity right where MMS saw an IDR. And then the bottom is where I put resistivity just across the whole tail around minus 30 RE. Then I've plotted the X lines. So the X-axis here is time. The Y-axis is X GSM, so how far in the tail it is. And it's colored according to its location in the dawn-dusk direction. And finally, the size correlates to how long the X line is in the dawn-dusk direction. And so what you see is for each simulation initially, which is to say before the substorm onset begins, which happens at this orange line, you get some small X lines far in the tail. And if there's no resistivity there, they just sort of peter out. If there's resistivity there or nearby, that X line sort of takes over. It becomes very extended in the dawn-dusk direction. Here, it's light blue, so it's off. It's not on the midnight, but it sort of shifts to the midnight and dominates the whole tail. And you have this huge X line that's reconnecting by the time the substorm onsets. But if you don't have resistivity there, that doesn't happen. With no resistivity, you see that by the time the substorm onsets, there's really hasn't been any substantial reconnection at all. In fact, reconnection doesn't happen until almost 20 minutes later. And again, it's very close into the near the Earth. But after that, it sort of extends across the tail and retreats tailward, as you might expect. When we place the resistivity where MMS saw an IDR, you get the reconnection, unsurprisingly, happens at that location, and it sort of moves towards midnight. This is on the dusk side, is where MMS saw the IDR. It moves towards midnight, and although it does get closer to the Earth, it never gets that close to the Earth, right? This is well within 15 RE, and this never quite reaches there. And then eventually you could say this is retreating tailward, and maybe it just breaks up, just like this simulation on the bottom. But in both cases, when you include the resistivity, you don't get these extended X lines near Earth. Instead, you get these much smaller X lines, right? They're just a few RE in width, and they don't last very long either. You can see that pretty clearly here. This one is just a couple minutes. If you say this is all related, maybe it's 20 minutes at most, but that's pretty that's a big jump. Right. So the current efforts that we're trying to do now is really incorporate the time dependence of the resistivity, right? Because these X lines in the tail are not stationary for the entire substorm. They jump around. And in fact, what we see from the data mining reconstructions are these X lines jumping around. So these are shown just as they were shown before: meridional plane, equatorial plane on the right, and these black lines show where the resistivity is located. And again, this resistivity location is determined from the data mining reconstruction. So you can really think of this region as where the data mining sees an X line. And so it's jumping around a little bit. It's evolving across the tail, as you might expect. And then here we're comparing the AL index, both observed, which is in blue, and then derived from the simulations, which are in green and red. Green, let's see, green is no, I'm sorry. Red is the one that should match blue exactly, if everything is equal. And green is sort of a super version of that, if you will. And I can go into the details, but for now, just focus on the red line matching the blue line. And the point is that just putting the resistivity in alone isn't necessarily going to make your simulations match perfectly with the AL index. And the reason for that is preconditioning. So if you don't include any preconditioning, and I'm noticing now that these titles are reverse, actually. The one on the right has been preconditioned, the one on the left has not. And what I mean by that is that you need to simulate your magnetosphere for some time before your substorm begins, because of course, the real magnetosphere has been around for a very long time. And so you can't just start with a dipole and some solar wind and hope that you're at t=0, you're matching reality perfectly. And the way that this comes into play with what we're looking at with this resistivity is that the tail of the magnetotail is not necessarily going to be stretched enough. And if it's not stretched enough, then your current sheet isn't going to be strong enough. And if you place resistivity somewhere and there's no current, it's not going to do anything, because of course in Ohm's law, it's eta J. So you need resistivity and current. And the hope is that with preconditioning, your tail becomes stretched a little bit more and you can see something a little bit more reasonable. And indeed, when you include some additional preconditioning, you get more of a response in the magnetotail when you include the resistivity, which is this red line, than when you don't include resistivity. And so that's what I'm trying to show here. But obviously, we're still not matching the observed AL index very well. And there's a lot more work to be done on this front. This is just an early attempt at including the full time-dependent resistivity. So as a final point, I want to just briefly mention, I'm not going to go over every detail here, but I just want to briefly mention an additional project that we hope to start working on, which is incorporating not just the empirical pressure, not just the empirical resistivity, but actually empirical thin current sheets. The idea being that in MHD, the kind of current sheet that you can get is not as thin as what is observed, right? So in reality, you get these thin current sheets which stretch out for many RE much more than what you can get in MHD. And so we hope to take these thin current sheets that the data mining reconstructions do reproduce and actually use that as a force on the MHD fluid to try and stretch out the tail a little bit more realistically. And of course, if we're using this to stretch out the tail, that also helps with our preconditioning issue, because now our tail is more stretched, we have more current, and the resistivity will be more effective. Okay, so just to conclude, data mining is capable of accurately reproducing observed X and O lines, as Grant showed in the previous, or whatever, last week, whenever his talk was. And when we place localized resistivity in those regions where data mining saw an X line, we produce X lines in those regions, which is an excellent agreement with both the data mining reconstructions and the MMS observations of ion diffusion regions. But interestingly, when you force reconnection to occur in the midtail instead of where it wants to occur much closer to Earth, we get a bunch of magnetic flux that's transported through the X line towards the Earth and actually prevents the current sheet from collapsing and reconnecting there. And so this makes our simulations more realistic in that sense. However, unexpectedly, the rebound flows from this midtail reconnection. They bounce tailward, they can stretch the magnetic tail just a little bit, but it can stretch it enough to reconnect, at least in our simulations, and create these small X lines, just a few RE in the dawn dust direction and very short-lived, minutes is sort of the time scale to think about them. But that was definitely an unexpected finding in this research. And then finally, when incorporating the full time-dependent resistivity, it may be important to also include thin current sheets that don't naturally exist in MHD, but do exist in the data mining reconstructions and in reality. And so by including these thin current sheets, we'll create more current where we need to put in the resistivity, which will then lead to X lines that agree with the data mining reconstructions. And I just want to point out that, a lot of this work has been published, at least all of the stuff where before the time-dependent resistivity, that has been published now, and you can find it at this DOI. Thank you.
Great, thank you so much. I really appreciate that talk. We now have plenty of time for questions for both Anthony and Harry. So feel free to either enter them in the chat or raise your hand and unmute yourself if you'd like to ask.
Let me just go first, and then thank you very much for nice talks and very interesting. And then so I'm not really steeped in MHD simulations, and I need better. Also, I'm coming more from exposure to tropospec DA. I find it very interesting because to make data simulation or for the model to accept constraints coming from observations, there are lots of things has to happen. So what I see is basically you try to mitigate dynamical imbalance that coming from both, and then I found it really striking that you keep calling empirical, just empirical rather than saying okay, so imposing some balance. For example, resistivity that Harry you just talked about, and Anthony's when you're actually trying to get that pressure information, but then flux tube size and all that. So I wonder that I understand that, but then in the tropospheric DA, we actually handle it in covariance, that when you ingest that, for example, the pressure, well, wind and then temperature, well, temperature and then pressure has to be balanced. And then they impose that balance actually in the form of covariance, and then to mitigate issues coming up. But I guess for MHD with the data sparsity, that is probably not the scope. Does that maybe, do you see that how your work kind of progress toward more sort of data assimilation like framework to incorporate dynamical constraints coming from observations?
Yeah, I think it's very difficult because, again, it's hard to ingest information at just a single point so much, just because, you know, it's hard to understand how that's going to affect the system as a whole. And then because you have pretty much all of your parameters are coupled together in one way or another, that can be very nonlinear, makes it very tricky for that reason. I maybe don't understand the covariance method enough to know if that's necessarily handled depending on how you do it.
Yeah, I guess that what I'm seeing is that I mean, maybe you're just calling the same thing in a different way in your field. So it's true that, you know, when you ingest the impact of one data point, even in a troposphere or in a other or more sort of the conventional DA method, we don't actually change the state, you know, model state at that point. We actually spread it out. So like, let's say that even you know, temperature measurements done, it's actually spread out the impact in winds so that there's no dynamical imbalance. Otherwise, those waves get you know, unphysical. The unphysical waves get generated and they make model crash and all that. So I kind of feel like you're actually trying to get there. And then maybe I was curious that if you see, you know, it's a great work. I find it very interesting what's happening there. But then I was just kind of maybe running ahead that, you know, this is maybe the beginning that you could actually come up with a really, you know, clever way of incorporating multi-parameter global scale constraint coming from very limited observations.
Yeah, that makes sense. I think.
Can I ask a question based on that?
Yeah.
Hi, this is Kareem. I just had a question in terms of, you were saying, I think the measurement or the input is spread out. Can you clarify how it's spread out, or like over what sets that spatial domain?
Yeah, so that is a work of, for example, coming from, for example, if you have like a ensemble model simulations, for example, and then we could actually compute the covariance between, you know, the given point. Let's say MMS go through, and then you want to spread that information out into the spatial domain, and then not just the parameters directly observed. So if it's pressure, then you know the relationship, just like you were saying in the talk, that these are actually, you know, if coupled, well, some impact of dynamics should be felt in the multiple parameters. You have information in the model. That's why you're correcting it, or you know the physics. So that's, I don't know if I'm explaining that. So
I think so. I guess one interesting thing is, you know, like for something like ring current pressure, if you get the spatial domain off a little bit because of the way that pressure will spread along a field line, you could imagine putting pressure, even if it's locally in one spot, that will then move along the field line and potentially get into very, very spatially different domain as a result, if you're off by a little bit.
Are you raising it as a potential to spread out the information, or are you raising?
Well, I guess it's just because of the magnetic field and how it connects the domain.
Right.
It's such a large spatial connectivity through the magnetic field that I guess you wouldn't get in the troposphere, which is much more dissipative and local.
It's yeah. Well, I think the physics is very different. So what you're saying is that I guess that spatial domain, I mean, I think it's coupled with the fact that there's a sparsely observed system, and in fact that the actual sort of the correlation it's really global, I guess. So that's probably the challenge. So I'm just I'm just trying to understand the scope of
it's interesting to learn more about how people do it and then how to apply
I
it
think there's something to learn about, so that I mean, time dependent adjustment, it's alluded in Harry's talk. I found it. I think that's what you want to do eventually, as a satellite flies through. So you want to kind of like keep doing it as anyhow.
Yeah, I think another difference here is that it's true at any given time there aren't enough data points, but through the data mining we end up or they end up producing a continuous analytic function of the magnetic field, which you can evaluate anywhere. And so that lets us calculate a pressure for every single point too. So when we actually get to the ingestion point, we actually have all the information everywhere. So there isn't, in that case, any smearing out that we really need to do. But yeah, there are those extra considerations, what that means dynamically, which is what we were talking about, and we just let MHD sort of handle that difference between the models. But yeah, I'm sure there are definitely situations where we don't have information quite everywhere, and we should use something like that instead, with its own considerations of how to bring that into the magnetosphere space.
Yeah, I found it really exciting that maybe the magnetosphere community come up with a very different way of doing this that I think we try to achieve, to sort of put that observational constraints in a dynamical, consistent way.
Yeah, sounds like a good conversation for a workshop where we can figure out if we're talking about the same thing or not.
Yeah. Yep.
Great. Are there any other questions for Anthony or Harry? Anthony, I had just a really quick one for you. I know we're at the top of the hour, but on your second to last slide, you showed the field line currents at 9 UT. I was wondering, and then you mentioned that basically different periods might have a better agreement than others. I was wondering if you had seen a systematic difference between empirical pressure ingestion during different phases of the storm, whether it was better capturing the growth phase or the main phase or recovery or other aspects, or if it was basically scattered in terms of when you saw the best agreement.
Yeah, for this specific storm, I didn't go through and specifically make note of when it did and didn't agree best. It did tend to agree pretty well once you got into the main phase of the storm. I can't quite remember how well it does on the sudden storm commencement. I wonder if Misha would like to comment just in general how well they end up reproducing certain phases. But I unfortunately don't have a more comprehensive answer for now.
Just barely caught your focus.
Oh, we were just talking about whether the field line currents agreed better in different phases of the storm than others. So I was going to say, I think in general, you found that the reconstruction performs better during certain phases over others.
Altitude magnetic field data perhaps from Ampere to further constrain the model and improve the field line current reconstruction. This is a very challenging task in general because the model architecture is not quite ready for accurate reproduction of the field line currents. This is a work in progress. Thank you.
Okay, cool.
Yeah, thanks, Misha, and thanks, Anthony. Any final questions? If not, let's thank our speakers again for their really wonderful talks. Thank you guys again for spending the time, and thanks also to Grant for giving a really nice presentation on the data mining product last month. I thought that was a really nice two-part series that we had. So thanks again, everyone. Please be on the lookout for our website for more updates on upcoming seminars and also for announcements on the workshop this summer. I think we had a really nice preliminary discussion. I'm looking forward to continuing that there. So thanks again. Hope everyone have a really great Tuesday and rest of the month.